catch rare fraud with meaningful metrics. By the end, you will know how to compute precision, recall, and F1 in Python. You will see why accuracy lies on imbalanced data. You will learn to pick a probability threshold and try F-beta and average precision to rank results. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Imbalanced classification shows up in fraud detection, medical screens, and rare defect finding. You have many more normal cases than positives. Success means catching true positives while keeping false alarms low. A model that labels everything as normal can still claim high accuracy and be useless. Precision, recall, and F1 give a clearer picture. They focus on positives and the trade-offs that matter in practice. At a very high level, precision is the share of predicted positives that are actually positive. Recall is the share of actual positives we found. F1 is the harmonic mean that balances precision and recall in a single score. For a quick mental picture, imagine a net that catches fish. Precision measures how many of the caught things are fish. Recall measures how many fish in the sea you actually caught. Fun balances those two goals. These metrics help when positives are rare and business costs differ between misses and false alarms. We will build a small credit card fraud toy pipeline. We will compute basic metrics, compare to accuracy, sweep thresholds to maximize F1, try F-beta to favor recall, and finally summarize ranking with average precision. Now we will compute basic metrics on our toy dataset. This snippet computes precision, recall, and F1 on an imbalanced toy set. It shows how to count true positives, false positives, true negatives, and false negatives, and then fold those counts into precision and recall. Precision appears as predicted positives that are correct. Recall appears as actual positives that were recovered. F1 combines them as a single balanced score. The snippet prints all three and also prints the raw confusion numbers so you can see where errors come from. This is the baseline check you always run on a new imbalanced dataset. Next, we will contrast accuracy with F1 to show imbalance pitfalls. This example contrasts overall accuracy with F1 to make the issue concrete. It sets up the same toy dataset and computes accuracy as the fraction of correct labels, then shows that accuracy can be high even when recall is near zero. The code varies the class imbalance, or a naive all-negative predictor, to make the divergence obvious. Changing the imbalance ratio or the baseline strategy will widen or shrink the gap. This demonstrates why you should not rely on accuracy alone when positives are rare. Now we will search for a probability threshold that maximizes F1. This code selects a probability threshold that maximizes F1 by sweeping thresholds across predicted probabilities. It evaluates precision and recall at each threshold and computes F1 to find the best trade-off for your objective. The snippet also plots or prints the top thresholds and their scores, so you can pick a threshold that matches business goals. Raising the threshold tends to increase precision and reduce recall. Lowering it does the opposite. The sweep helps you choose the point that balances false alarms and misses in the way you prefer. Next, we will compare F1 with F-beta to emphasize recall when needed. This snippet compares F1 with F-beta, where beta weights recall more or less than precision. It computes F-beta for a beta greater than 1 to favor recall, which is useful when missing a positive is much costlier than a false alarm. The example shows how the chosen classifier or threshold changes when you optimize for F-beta instead of F1. Adjusting beta moves the optimal threshold toward higher recall as beta increases. Use this when business cost or safety demands that you prioritize finding positives over reducing false positives. Finally, we will summarize ranking quality using average precision. This example computes average precision to evaluate how well the model ranks positive cases higher than negatives. Average precision approximates the area under the precision recall curve and is a single number that reflects ranking quality across all thresholds. The snippet sorts predictions by score, accumulates precision at each true positive, and reports the final average. This metric is helpful when you will review a ranked list or set a cutoff later. Improvements in probability calibration or model confidence should raise average precision. Recap: precision measures predicted positives that are correct. Recall measures actual positives that were found. F1 balances the two, and F-beta shifts that balance toward recall. Use these metrics whenever your classes are imbalanced and you care about catching rare events. One caveat: picking a metric without tying it to business cost can lead you to optimize the wrong trade-off. Next step: run a threshold sweep with cross-validation and optimize the F-beta that matches your business cost. Then measure average precision on held-out data. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.